Okay, we're going to go over what's known as locations. We're going to talk about the locations on this curve are these curves where the function is not differentiable. Okay, we talked about these things. I want to review this concept with you guys. So a function's not differentiable. Remember, when you have a vertical asymptote at that location, at the location of a jump discontinuity, at the location where the function is not smooth, meaning there is a sharp corner, or where you have an infinite tangent. These are the only places, locations, values of a, where a function is not differentiable. And that's what we're looking at. Where is these values here? So remember, we would say at x is a, where you're not differentiable. Okay. So you're looking at this curve, y equals sine minus 2 cosine x over the restricted domain of 0 to 2 pi. So when you look at this picture, what I want you guys to do is know this. Are there any vertical asymptotes down here? No. There's no vertical asymptotes on your curve. Is there any jump discontinuities? The answer is no. Are there any sharp corners here? No. Is there an infinite tangent, meaning is there a portion of the curve that is vertical? The answer is no for all of these. Therefore, this is differentiable everywhere. So this is differentiable over your interval. I think that was 0 to 2 pi. So it's completely differentiable over those values. And let's double check something here. Let's spell it out. So you're differentiable over the domain that this function is defined. And I think you want to kind of understand a few things too about sines and cosines, right? Those are nice smooth curves. And I'm just going to kind of mention that to you. Nice smooth curves. And it doesn't have any of those things that we're looking at, okay? Looking out for. So we're going to look out for these things. You got a nice polynomial function, and it looks like it's smooth everywhere, this polynomial function. And notice there is no vertical asymptotes. So, I mean, we might just go back and just say, okay, how about this? There's no vertical asymptotes. There's no jump discontinuities. There's no sharp corners here, and there's no location on the curve where it looks like there's a vertical tangent. And it's a no everywhere again, so this function is, in fact, differentiable. Everywhere. So when it's differentiable everywhere, that's really all real numbers. And then let's talk a little bit about the interval notation. Because if you're looking back at your book, you might see this kind of notation, like over here, this function is differentiable over the interval that it's defined, the restricted domain, from 0 to 2 pi. And in terms of interval notation, that's 0 to 2 pi here. So you might see that as well. So far, these are some very nice I would say smooth curves, beautiful smooth curves, polynomials, and combinations of sines and cosines, at least in terms of addition and subtraction. So this also is interesting. And let's kind of be consistent. That's a no here, a no here, a no here, and a no here. So this is what we're looking for, okay? We're reviewing the ideas we went over in class. All right, let's take a look at some more curves. And if I said to you, okay, here's another function. Y is 1 plus x, plus 1 over x squared, and 1 plus 1 over x plus 1 over x squared. The second you see a function that has denominators, like you see here, remember, you got to worry about that. It's the location. X is 0. The other one is x squared is 0, which implies x will be 0. If you guys recall, these are the locations where you have vertical asymptotes. And your functions they're not differentiable at the location of those vertical asymptotes. So this is a yes. You have vertical asymptotes at x equals 0. There is no jump discontinuities in this curve. The function's smooth. There's no sharp corners. This is what we mean by that. You don't have a sharp corner. The function is nice and smooth. And there is no locations on the curve that have what we call a vertical tangent. The curve is not vertical anywhere. Only has a vertical asymptote at x is 0. So if you said, where is it not differentiable? At x is 0. So this curve y, or if we call it f of x, okay, we can say the curve f is not differentiable at x is 0. So it's differentiable everywhere else, but x is 0. And so what that looks like is in interval notation, you throw out 0. So it's differentiable everywhere else for all real numbers, but you're going to throw out, you're going to minus that point 0. Throw it out. And that's really what we want you to notice about this. So, okay. Now, the next curve, this function, and typically functions with rational exponents you have to be concerned with, because they may have this location right here that we want to emphasize. That is a sharp corner. So this curve does have a sharp corner. We say this is not smooth. That's what we mean by not being smooth. So is there a location where that function is not smooth? Yes. Has a sharp corner? The answer is yes, and that is at the location x is 0. You have a corner, a sharp corner. It's not smooth at this location, and that's what we mean. That's almost, in some ways, the essence of not being differentiable. Being differential means your curve is smooth, like in these locations here. This is nice and smooth, ladies and gentlemen. There's no sharp corners. This is nice and smooth. There's no sharp corners at all. There's corners, but they're not sharp. Corners, but not sharp. This doesn't have any sharp corners. It's smooth, except there's a vertical asymptote at 0. This is smooth everywhere, but at this sharp corner at 0. That's where it's not differentiable. So is there vertical asymptotes? No. Are they jump discontinuities? No. Infinite tangents? No. So F is not differentiable at x equals 0. So where is it differentiable? From minus infinity up to 0, union 0 to infinity. So this is kind of just remarking about this. We'll probably look at another video that has that information. Okay? So rational exponents, fractions that have, your powers are fractions. They are issues. And as you guys can see in this case, there's a yes for not being smooth, having a sharp corner. All right. Y is sine squared. Guess what? This is nice and smooth on the domain that it's defined for. They define this y is sine squared on this interval from 0 to 2 pi. So this is nice and smooth. Okay. Are there vertical asymptotes? No. Jump discontinuities? No. Is there any sharp corners? No. Places where it's not smooth? No. Infinite tangents? No. We'll see an example of an infinite tangent. It's where the curve is virtually vertical. So this is a nice situation, sine squared. And, it's differentiable everywhere. I'm going to write that down. You say differentiable where? It's everywhere it's defined. It's defined on the interval from 0 to 2 pi. So it's differentiable from 0 to 2 pi. Okay, if we write that interval down. A nice polynomial function. This polynomial function is nice and smooth. It's smooth everywhere. Now, there's no restricted domain, so this is actually smooth for all real numbers because there's no restriction on the domain. Okay, that's a smooth curve. Polynomials, ladies and gentlemen, are the examples of smoothness. Nice rolling hills. There's no vertical asymptotes. There's no jump discontinuities. There's no sharp corners. Locations where it is not smooth, sharp corners, this answer is no. And there's no infinite tangents, meaning the curve is never vertical, up and down. We will see an example of that, but polynomials are really nice. They're nice and smooth everywhere. And we mean everywhere, we mean all real numbers. So that's kind of if you want the interval for all real numbers here, that's negative infinity to positive infinity. That's what all real numbers mean. Okay, nice and smooth. All right. 7. This is number 7. Weird. Now, you have rational exponents, and I want you to see this portion of the curve right here. Because you might say, hey, Mr. Judge, is this smooth? And yeah, it's pretty smooth. I want to say there's no vertical asymptotes. There's no jump discontinuities. Let's put down the word no. No vertical asymptotes, no jump discontinuities. There's no locations where you have a sharp corner. However, this is an example where you do have an infinite tangent. Let's take a closer look at this. What does that mean? Well, for us right now, it's right here, meaning this portion of the curve here. Okay, I'm going to find a point here. Let's get a pencil, not a highlighter. At this location here, this value of x, when x is 0, you see this curve is vertical. This is what I mean by that. Up and down is vertical. It has to be strictly up and down, not slightly up and down, strictly up and down. And at that location, you do have, when x is 0, you have what we call an infinite tangent, meaning you got a tangent line at this location here. And we'll see more of that idea in the future. And I want to try to draw an arrow. Doesn't let me. But okay, here's my arrow. So you do have what's called a vertical tangent line. A way to see that on the curve is the curve has to be vertical as well. So this is the location I want people to really zoom in on, right in here. Okay? And that occurs when the value of x is 0. Now I'm going to erase all of this so you can get a good look at what I'm talking about. Okay, the curve is virtually vertical around here, up and down. Okay, so, and that happens at x is 0. So we don't know the y-coordinate, but we don't need to know the y-coordinate. We're just saying, you know what? Our function f, if we call this f of x, right? This is your f function, your curve. F is not differentiable at x equals 0. So it's differentiable. It's nice and smooth everywhere, except at 0 we have a infinite tangent. So we throw out 0 again if we're going to look at interval notation. Okay, you're going to throw this out. So this is an example of what I'm referring to, and that's really number 7. Okay. Now, number 8 is defined for all real numbers. This function, notice again, you have a rational exponent. This is what I'm referring to, that the power there is a fraction. You got to be concerned with those functions. Because at this location, you have a sharp corner. This is where the function is not smooth, ladies and gentlemen. It is not smooth. You definitely have a sharp corner. So let's write that down here. So at this location, that happens at x is 0. Right? There's your location. You got a sharp corner there. What that means is there a location where the function is not smooth? The answer is yes. Not being smooth means you have a sharp corner. There's no vertical asymptotes. There's no jump discontinuities. And there's no infinite tangents. But you do have a sharp corner there at x is 0. Now let me erase this so you guys can see a little bit better. But that's what we mean by it's not smooth at 0. Sharp corner at 0. All right, that's number 8. Oh, let's continue. Your function f is not, I'll say, differentiable at x is 0. Again, we throw that value out in terms of interval notation. Just throw out the 0 value. And that's what they're looking for. All right, look at this. Nice sines and cosines. Boy, this curve has a restricted domain from negative pi to pi. This curve looks nice and smooth everywhere. This is a nice smooth curve over that restricted domain. Okay. Are there any vertical asymptotes? No. Any jump discontinuities? No. Sharp corners? No. Infinite tangents, locations on the curve that are vertical? No, there's no vertical up and down. So this function is differentiable everywhere. And let's kind of spell that out, I guess. Differentiable for everywhere, meaning for all real numbers. All real numbers in interval notation, and it's negative infinity to positive infinity. Number 9. Nice and smooth everywhere. That's beautiful. Sines and cosines, like polynomials, are nice things happen with them. Now here's again a sort of rational-ish function. Y is x over the square root of x squared plus 4. However, I want you to notice, just because it's a rational-ish, that denominator is never 0. So you might be tempted to say there's vertical asymptotes, and you say, okay, that's going to happen where x squared plus 4 is 0. You can say, well, can I say it's a square root of that? Yes, and that'll imply x squared plus 4 is 0. That does not happen. This never happens for real numbers. You'll get complex solutions. So trying to solve this gives you complex numbers, meaning you get x squared is negative 4, x will be plus or minus 2i. This is not calculus of complex numbers. We throw this out. It's calculus of real variables. So there's going to be no vertical tangents here. So this means you have no vertical tangents, okay? Sorry, vertical asymptotes. You got no vertical asymptotes because the denominator could never be 0. So, okay, no vertical asymptotes, and we don't see any in the curve. There's no jump discontinuities. It is smooth everywhere. There's no sharp corners. And there's no portion of the curve that's strictly vertical up and down. So it's a no, no, no. And again, you got a nice, beautiful, smooth curve. And that's true for all real numbers. So this is going to be, we say the function f is differentiable everywhere. Everywhere means all real numbers. And then the interval notation for all real numbers is negative infinity to infinity. So just giving you some nice, beautiful examples of differentiability, and that's what we're doing. We're trying to find locations where it's not differentiable. All right. Number 11. Okay, this is interesting here. And yes, this is all real numbers over here. And let me go back. I apologize. No, this isn't all real numbers. It's not differentiable everywhere. Let's go back. We made a mistake. This is only defined from negative pi to pi. So, all right, it's differentiable over the domain that it's defined for. I caught my error here. I caught this here. I caught the error there. So it's only defined for, come on, from here to here, really. This isn't. All right. Apologize. Just subconsciously something told me something was wrong, because when I seen this tangent curve, it's a very similar domain here. Okay, this tangent curve is defined over, again, a restricted domain. And yes, they do have vertical asymptotes. The answer is a yes. If you look at this picture, yes. Jump discontinuities? No. Sharp corners? No. Infinite tangent? No. These are the locations where it's not differentiable, but we do have vertical tangents here. Vertical asymptotes. I keep saying that. I have that on my mind. was going to make a video on that, but all right. So it does have these locations. Where are they, though? Oh, tangent squared. Well, go back to the idea of what tangent. Right tangent is, this is y equals sine over cosine, because that's tangent squared. So using algebra, this is actually sine squared over cosine squared. And where is cosine squared equal to 0? We can set that equal to 0. Cosine squared equals 0. Well, that means cosine is 0. So we have a trig equation. We got to find where cosine is actually 0. And we got to consider that over the restricted domain from negative pi to pi. So cosine is 0. I'm going to go back up here and remind you guys about these curves that I said. It's really important for you to know some trigonometry. Like cosine is 0, what does that curve look like, right? So this is 1, negative 1. I'm going to think about this. I'm going to deduce my answer by considering the cosine curve. That's going to help us here. Now, cosine starts at the highest value, goes to an intercept, lowest value back at the intercept. So I'm going to see, this is one cycle of cosine. This is the cosine curve. I'm looking for where cosine is 0. So I'm looking for the intercepts. Cosine is 0 here and here. So cosine is 0 at x is pi over 2. But remember, cosine is symmetric about the y-axis. And if I go now, consider the portion of the curve to the left of that y-axis now. Negative pi over 2 goes over here. You got your intercept. And you're going to get down to over here. This is where pi is. The function is defined from negative pi to pi. So let's remember this. Okay. This is my restricted domain. So if you said, where are the vertical asymptotes while you're looking at them, it happens at x is negative pi over 2 and positive pi over 2. Okay, this is where you have those vertical asymptotes. So this here is negative pi over 2 and positive pi over 2. So you might say, how do we answer the function, the question, where is it not differentiable? Well, the function is not differentiable at x is negative pi over 2 and x is positive pi over 2. That's the location of your vertical asymptotes. You know, solving that trig equation and considering the curve here. Okay, I know we're going backwards, but all right. So as interval notation, though, you're going from negative pi to pi. So what does that look like? Interval notation means we start at negative pi, and as we go to negative pi over 2. We got an open circle, open interval. Negative pi over 2 to pi over 2, open interval. Union from pi over 2 up to pi, close interval. There you go. All right. Nice piecewise function. This is a function f. Now, it's hard to see, but this function looks to me has a vertical asymptote right here at x equals -1. So yes, this is the location where it's not differentiable due to having a vertical asymptote. It's not differentiable at this -1 location here. Okay. Does it have a jump discontinuity? It sure does. Right in here, let me get this out. This is the jump discontinuity. Okay, so this is a yes. So if I change my colors, that happens at x is 2 over here. Right? X is 2. You have a jump discontinuity. Okay. Yes, at x is 2. We're going to bring this down here maybe. Okay. Do you have a sharp corner anywhere? Let's get out the orange. Yes, we got a sharp corner here. It's not smooth. So yes, a sharp corner happens at x is 1 here. This is a yes at x is 1. Any infinite tangents? No, I don't see locations on the curve that's strictly vertical, so this is a no. And so we're just going to answer this way. We're going to say, okay, your function f is not differentiable when x is -1, x is +2, and x is +1. It's not differentiable for these values of x. So take a good look at this. So it has 3 out of 4 of the problems that we're looking for, and that's that. I don't think I'm going to write the interval notation for it, but there's 3 locations where it's not differentiable. All right. Hope you enjoyed the demonstration.